If not, on Tuesday.
Okay, let's just get started. It's just past 6:30. So I'm just going to go through the tests and just like the general things that you probably should know about the test. And if you guys have any questions, you can ask me. I can't pull up any output, which kind of sucks, but we can make do. So with multiple regression, that's the first thing we went over in class. Very excited about multiple regression. We have our assumptions. We have normality, linearity, homoscedasticity, which is even distribution of errors across all levels of IV, so all groups, and independence of observations, and perfect measurement. So is independence of observations robust to violation?
No.
Is the normality?
Yes.
Okay. So what kind of CVs do we want for our variables?
What kind of what?
So what kind of relationships, what kind of correlations do we want between our variables if we're thinking in terms of independence of observation? We want something between 30 and 60%. So you want it to have some correlation, but not too much, because otherwise it'd be multicollinearity would be a problem. If there's too much overlap. If there's too little, your T's, if there's too little, there's too much standard error. Your T's will be too low. You would not get significance when there is, which would be type 2 error. Yep.
Can you do that again?
Too
low.
T's too low, not significant, increased type 2 error.
Is this independence observations you're talking about? Or?
Well, I'm just talking about multicollinearity, which is related to independence of observation.
Okay, so you're talking about the tolerance, 30 to 60%?
Not necessarily, just like the relationships between the variables. Yay! Welcome.
What did I do?
What? Hi. We're just starting pretty much. We're just doing multiple regression.
Okay.
Okay, what else? So there's for normality, you want to look at outliers. Possible causes of outliers would be just unwanted, unusual events, or people with amazing abilities. Maybe they just do really well, or they have no ability. Unexplainable. There's also multivariate outliers. And how do we look for multivariate outliers? Mahalanobis. That's one. Those other ones. Cooks and DF beta and leverage. So Cooks, leverage, looking at the whole model. We have DF beta. And so that would be each predictor. If we have multiple predictors, it's going to be how if you take out each of those sample or like scores, how each of those predictor slopes are affected. So you're going to get, if you have 3 predictors, you're going to have 3 columns for DF beta. And the more it's affected, the more that point of data affects that predictor, I guess. Let's see. Do you have any questions about multiple regression? I mean, we've been kind of going over it for a while. R squared is equal to sum of squares of regression over sum of squares total.
And R squared change is the same as the semi-partial squared. We said that in class.
Yes, you did say that in class. R squared change is the same as semi-partial squared. What does R squared change, guys? You guys remember?
He just said it too, but I don't remember. I remember he said it.
You put in predictor, and then you put in more predictors.
Uh-huh.
So it's like the steps or the blocks in the regression, the difference in the R squared.
Yeah, so that change that occurs from one predictor to the next is R squared change. And that's good to know. Hey. Yeah, it is. So we have so where do we look for specification errors? There's a nice graph that tells us information about a bunch of assumptions. Yeah.
Yeah.
And standardized. Predicted value. You should be writing. You have better handwriting than I do. How does that look?
Bad.
Why is it bad?
Because it's making a
There's a pattern.
Curvilinear.
Yeah, it's a curvilinear. How about that one?
That's good.
Because there's no pattern. So yeah, we look at our residual plots, and they tell us about outliers, because you'll also have like 1, 2, 3 standard deviations. So if it's like really low or high, you know that these, if it's like greater than 2.5.
Okay.
About 2.5. Then you know that you have an outlier here.
Yeah, plus or minus 2.5.
And so yeah, standard error of the estimate is also another name for standard deviation of the residuals. Standard error of the estimate is the same as standard deviation of the residuals. So this is standard deviation of the residuals. What's the residual?
Error.
That's right. Okay. You want anything to add? Okay, Durbin-Watson?
2. 1.4 to 2.6. 2.
Yeah, good.
1.4 to 2.6.
1.4 to 2.6.
Index of autocorrelation. So it also tests independence of correlation, independence of observations.
So
So that's what I was talking about in regards to multicollinearity, not the tolerance in regards to regression.
1.4 to 2.6 is what?
Is the range that we want our Durbin-Watson
That's
within.
the range.
Mm-hmm.
So about 2.
Close to 2.
About 2, but as low as 1.4, as high as 2.6.
0.2, that's bad.
You said
0.2? Yeah, 0.2 is bad. Low.
0.2 is bad. Okay. Where are we?
We are. What's the B weight?
Unstandard at raw.
Mm-hmm.
Okay. For B weight, you would say like 1 unit increase in X predictor produces blank unit increase in the DV with the other variables held constant, and that blank unit is the B weight.
1 unit increase.
I don't have an output here.
Yeah.
So yeah.
The predictor creates a Y change in a DV with the other predictors held constant.
Uh-huh.
What? A 1 unit increase in X predictor creates a Y change in the DVs with the other predictors held constant.
So say the predictor was anxiety. 1 unit increase in anxiety produces, I don't know, 2.45 unit increase in test scores with other variables held constant. Okay? And you guys should remember that from the graphs and the tables and stuff. The beta weight is what in comparison to B weight?
That's the standardized.
Mm-hmm. So how is that helpful?
You can compare the predictors things.
Yeah. So how would we say that? Like in a sentence, like what I just used for the B weight, but for beta weight. Say we had a beta weight like 0.8. Anxiety is the predictor. Outcome is test score.
So an increase at 8. Well, you said it was a 1 unit increase in anxiety creates an 8 unit increase in test scores with all the other predictors also.
Low, but we're using standard deviation units here for beta weight.
Okay.
So 1 standard deviation increase in anxiety produces 0.8 standard deviation unit increase in test score with the other variables held constant.
Wait, so they are held constant?
Uh-huh. But you can look at, if it's one is 0.8 and one is, 0.01, and you can see, you can compare those two beta weights and see, which is a little more important.
I love Laura right here.
I'm going to read that. I'll try to write better. Nodded.
I have tolerance is equal to what equation?
1 minus what?
I heard something. 1 minus r squared, yeah. That's the collinearity between all the predictors.
That's error. No.
And so we want it to be as close to 1 as possible. The closer to 1, the better in the output. Should be 1. Semi-partial, or part squared in SPSS would be semi-partial, squared semi-partial, sorry. So that's the unique variance accounted for by whatever variable with the other variables held constant.
You're using variable and predictor interchangeably, right?
Yeah, pretty much. Just like reading off what I wrote here. It's not always complete.
It is part in SPSS, right?
Yeah, it's part. And you're going to square that to get the squared semi-partial. We did our swim statistics, la la la. Homogeneity of variance.
About the Pearson. Oh wait, are we there yet?
What? The core of the.
How he's going to ask them about that? Probably.
Yeah, we kind of went over that earlier.
You already went over.
Well, no. We were looking at the test, and so this test question says the variance in common between couple communication and attributional style is. So when you're looking.
Look at Pearson.
Yeah, look at Pearson and square it since it's the variance common. Yeah.
Variance in common. Yeah.
Any questions about any of that stuff?
You were going to say something about homogeneity of variance.
Yes, you were. Yeah. So how do you test for homogeneity variance? And? Well, if we're just looking at multiple regression. So we have Levine's, we have our F max, super old test from last semester. We do have a residual plot still, that tells us. Also Brown forest size, but we haven't really looked at that on output. So what's F max again?
The bigger variance over the smaller. What?
Variance.
Oh.
So largest variance divided by the smallest will give you F max. We have Brown's fourth size, and then this guy, residual plot, and Levine. Okay. I don't know, what else do we need for multiple regression?
You said this is the largest standard deviation squared and the largest variance.
The variance, you can, a way that you can calculate the variance. Is standard deviation
remember
squared.
that. That's also old. Variance is equal to standard deviation squared.
I don't know.
All right.
I think you put it on the last final, but maybe not this one. Oops. No.
We have adjusted R squared, which is more reliable than the R squared. Do you guys remember what adjusted R squared is?
So the variance comes from adjusted.
But why is it different than the R squared?
Yeah, why
What's
is
the
it different?
chance removed from it? Variability caused by chance is removed.
Why?
Well, it's a better estimate for the population because it's cross validation, and so there's shrinkage.
There you
yes,
go.
when you take your model and you apply it to another population, so that it's left. So it's adjusted for that cross-validation.
So it adjusts for the shrinkage, or the shrinkage is good?
No, it adjusts for it.
It adjusts for it, yeah.
So wait, we're talking about adjusting
Shrinkage
our square,
is bad.
which is what we actually use.
We use our
bad.
Yeah, we use R squared for analysis, but for the population, a better estimate would be adjusted R squared for the population at large.
Because your R squared is just for the sample that
Mhm.
you're running the analysis on.
But it would be like applying your data, your numbers and everything to the outside your research.
Yeah.
Okay.
You hot, Laura?
Kind of fun, yeah.
Okay, I think, well, we could do suppressor and
Yes, please.
Oh my God, I don't know if we draw this circle. I always forget that there's a little done.
well, we actually went over one of the test questions and it was helpful in explaining suppression.
you totally cleared it up for me.
So if you guys have your test and you look at number
23,
Number 23. No, not that. Oh, yeah, number 23. Okay. So, this is based on the above correlation. You guys all have your test? Yes. Based on the above, do you want to get yours? Based on the above correlation matrix, if IV2 were entered after IV1, the regression weight for the IV1 would what? So what do we have here with our relationships? We have a 0.73 correlation between the DV and IV1. So here's the DV, and let's say the IV1 is like 0.73 correlated. So it's a pretty high correlation. And then what's the relationship between IV1 and IV2? It's 0.87. It's also a nice strong relationship. We have IV1 and IV2. I'm using the Venn diagram to show how related each of these variables are. What about between the DV and IV2? There's only a 0.1 correlation, so it might actually be like that or something. So if we have these two entered into the model, we have DV and IV1, and then we enter IV2 in, what it does is it takes up this unwanted variance that's left out of IV1. So this relationship would go up.
Mm-hmm.
Does that make sense?
So it takes out like...
Because it says here that...
It takes out like the bad variance. So
Yeah.
if you can see this black part,
Why is it
it's
bad?
not, because it's not explaining any of the relationship of IV1 to the DV.
So because there's no relationship between IV2 and DV, the relationship between IV2 and IV1 that has no DV is bad?
No. So like, okay, so look at the part of the circle, this part.
Yeah.
So, okay, so if you take the whole IV1 circle, so if you add in IV2, now you're taking away this whole part of the circle.
This is like error right here.
Yeah. So it's like
every-
stuff you don't want.
All this stuff is error.
Because you want to explain this part.
Oh, 'cause that's...
Yeah, you want to, like, because that's the part where the IV1 relates to the DV.
So really...
So if you're taking away this error part, it's strengthening this relationship.
But IV2 has no relationship to DV right now.
Mm-hmm.
Right, but it doesn't matter because it's just taking away bad variance from IV1.
Yeah.
So it's like deleting this part of the circle. So then there's less kind of like not related stuff to the DV.
That's my relationship.
So this is the suppressor.
Yeah.
IV2 is the suppressor. So it's going to be a suppressor when you have a strong relationship between two predictors, a strong relationship between one predictor and the DV, and a really weak relationship between the DV and the other independent variable.
Right. So that when you add the second independent variable into the equation, its relationship is strengthened, the relationship between IV1 and the DV.
I see.
I don't know.
Someone giving up.
Yeah.
on the concept.
So, hold on, let's say this again, please.
You said the strong relationship between two predictors and a strong relationship between, can you finish that sentence?
So there's a strong relationship between the two predictors. The IV1, IV2 is a 0.87. That's strong. There's a strong relationship between a predictor, IV1, and the DV. So that's 0.73 here. And a very, very weak relationship or no relationship between DV and one predictor. So it's IV2 on here and IV2 and the DV have a 0.01 correlation. So those are all the ingredients you need for a suppressor effect.
So what's being suppressed is the IV2?
Well, actually what's being suppressed is, I think, I don't know exactly what the term refers to, but I guess it's suppressing the error here.
This is my new picture.
Okay. Yeah, it's deleting the error.
Yeah, so it's like if all this is error and it's in your equation, it's deleting this part. So so it's better. You're explaining more.
Mm-hmm.
Yeah.
It's reducing the error.
What's reducing the error?
This IV2, the suppressor variable.
Because you're entering it into the model. So the model as a whole is being affected.
It's like a sponge, and you put it, or like a hand towel, and you put it on the floor, and it takes up some of the water, and so some of the water is still there, but it
doesn't add anything.
It's not as much
Right,
that was there
it's taking stuff
before.
away. It's taking-
The water
It
is
isn't,
there.
okay.
It's taking bad stuff away.
IV2 is not adding anything different to the DV.
No,
No.
because it's not related to it. Yeah, because it's only related to the IV1. So that relationship, that relationship is the sponge. It's taking away the badness.
Sponge, that's good. That helps.
And then there's more yay. So, that's my picture.
Okay. So we okay on suppression? Hopefully. Only one question.
Yeah,
maybe less.
Maybe one question on it.
Huh? That's going to go up, like Richard Gardner's going to put that up, wherever he puts
This
his
happens
stuff.
going to really happen.
Well,
Yeah.
I'm going to watch what we're saying right now. But, yeah, it should happen.
I'm glad you're on
Richard, I know you can do it.
You're not on camera.
Let's see.
We did suppression. I think we would have.
Can we talk about partial?
I'm just going through my notes from last year.
I'm sorry?
Can we just talk about partial and semi-partial? Right?
Yeah.
Can we or did we?
I think we did.
We did score semi-partial. And that's the unique variance accounted for by the by the predictor when other variables are held constant.
So why is the relationship between X2 and Y with Y1 partial out of full? Why is that a partial and not semi-partial? Number 26. I mean, why is that? Yeah. Why is that partial?
So I have this written down. Semi-partial. The semi-partial is just partial out of X2. So it's just the amount partial out of X2.
Because it only. Okay.
So yeah, it's
Is
better.
X2
It's better with the circles.
Is it? Let's see what it was.
No? Yeah.
So I mean the partial is when x2, let's see, x1. So x1 is parceled out of both, would be a partial. Both predictor and outcome. And then the partial is when it's only parceled out of the other predictor. Right? Did I get them backwards?
Wait, you got it backwards.
I did?
Wait. Yeah. Semi-partial is just partial out of X2. Yeah. Yeah.
Yeah, I got it. Yeah, sorry. So semi-partial, sorry guys.
Oh, yeah, that's right.
Is when confusing you. So it's when the predictor is just parceled out of the other predictor. Partial is when the predictor is parceled out of all the other predictors and the outcome variable. Partialed out of.
So the partial is like partial out of everything.
Yeah, it's partial out of everything. Semi-partial, partially partial. Halfway partial. Pseudo.
That's a good way to remember it. Okay. What else?
Are we done with multiple regression?
We're done with this.
We can revisit if you guys have questions.
Is multiple regression?
That test is multiple regression and factor analysis.
Factor analysis.
Yeah. I don't know my factor. Which
I
one
can
are we
do
gonna do
complementarity also and have it down here.
That's just more specifics about.
Yeah, it's more. He's probably not going to do that.
He's not gonna
Suppression is good enough.
Yeah, he'll just ask about suppression. If he even asked about that.
So what would you use, like a hierarchical regression as opposed to like a stepwise or simultaneous? You guys know what those are? Know the difference between those?
How you're making that?
Yeah, hierarchical is like when you have a theory. So the person, like the human, is deciding the order.
Right.
Simultaneous is when you just put them all in at once. The stepwise regression, which can be automated by the computer sorts it and picks out the best variable. So the computer does it for you in a stepwise manner.
Right, but the hierarchical is when you have a certain theory about like things that go together in your data. So when you put them in blocks to control for certain things. So like if you put your demographics first, oops, that doesn't start with a B. Demographics. And then you're controlling for those, so those go in block 1. And then, and then you put in in block 2, you put in what you're interested in, so like depression, BDI score.
Okay.
Good,
I think we're done with multiple regression.
So we do the factor one now? Factor analysis?
Yay! Factor analysis. Okay. Yay. You heard me. Let's get my factor analysis one.
What's the difference?
Total what?
Things that we're going to
Oh, we're just going to go over everything.
I don't know. You guys are supposed to know that.
Well, there's factor analysis, and we have
Logistic, discriminant,
ANCOVA, ANOVA.
All right, so we'll keep going.
Yes, let's do that.
Okay, so confirmatory versus exploratory. Just those.
Confirmatory is when you have a theory, and exploratory is when you're just looking at a bunch of stuff and creating latent variables. Yep.
Yeah, exploratory is you're trying to figure out what a structure is, and confirmatory is you're trying to figure out, if that structure is really, what somebody already said it was, confirming the structure.
So what's the difference between a factor analysis and a principal component analysis?
Are you going to draw the...
Shared variance.
Which one has
Factor.
Good.
I don't even know where this is.
Yeah, you told me that's why I remember.
So if it was shared variance, what would you have on the diagonal in
Less than 1.
less than 1? So
Factor.
0.78, 0.65, 0.3.
What you're drawing right now is principal component analysis?
No, factor
analysis.
analysis. So it accounts for the common or shared variance in the factors.
So since it's the shared variance, only the shared variance, these are less than 1 on diagonal. Oh, that's piece here. And then principal component analysis when you include all the variance. That's why there's 1 on the diagonal of this variance covariance matrix.
Okay, these are 1. And these are
Oh, those are actual ones. I'm sorry.
Yeah, those are actual ones. Okay. So these are, yeah, great.
Okay. And then what kinds of rotations can you have?
Veramax?
Which is what type of rotation?
What
Or
category?
orthogonal or oblique, I don't know.
I think Veramax is orthogonal.
Orthogonal.
And what is an orthogonal rotation mean?
It's not correlated?
Yep.
There's zero correlation between the variables. So it's like a 90-degree angle when they do their rotation.
Yeah. And then the opposite of that is the oblique. Sharon already said it. Also called Obermann, whatever. And that means that you're assuming that there are correlations between the variables.
Okay. So you need a large size, sample size in these. Sorry.
Can I ask a question?
Yeah.
So oblique is when it's correlated. So how come for question number 6 on this test, it says that the correlation is near 0. So isn't that like no correlation? So then
Number 6. If a correlation matrix between the factors and these factors or components correlated near 0, you would call the rotation orthogonal.
Orthogonal.
Because there's no correlation. Okay. That's okay. Second chance, final exam. What were you?
Eigenvalue, what's that?
Also, you know,
I forget,
so
but you wanted to
just correlations. Do they also know about it? Besides it, you have correlation.
Oblique has correlation.
Is that all these know?
Yeah, for comparing oblique versus orthogonal, yeah.
Where's Veramax in it?
Veramax is a type of orthogonal rotation. So when you look at SPSS, they're going to have different, there's like Veramax, Quartermax, Obermann, there's a bunch of them, but they all fall under like these two categories. And it gets more complex, but we're not really going to go into that.
Yeah, that's not
stuff.
important. Just know the basics.
What'd you say? Eigenvalue?
Eigenvalue.
Okay.
Correlation for loading.
I know it needs to be greater than 1, then you like keep that component, but I don't remember exactly.
Based on Kaiser.
Yeah, it's Kaiser criteria.
Okay.
That's the Kaiser criteria, yeah. So eigenvalue greater than 1 is the Kaiser criteria.
But you could also look at what else, if you to determine the number of factors you want to keep.
Yeah.
Screen. Oh, you said it. Okay, so the scree plot, yeah. So kind of where it starts to level off is maybe where you would want to cut it off. You use your eigenvalues. You could also look at the percent of variance that's accounted for by those components or factors.
I'm allergic to that.
I think the cutoff is it 50%?
Yes, for the percent variance.
Yeah.
Yeah.
Okay, 50%. So if all your components account for 50% of the variance, you would also use that as a kind of a cutoff too. So you use all 3 of those to determine how many factors you want to use, and also kind of thinking, well, how many make sense? Like, do I have a scale of like 10 items? Would I really need like 3 different components for that, or not? That's also up to you.
All right. And so eigenvalues are the sum of the loadings squared.
So the loadings,
The factor loadings, or is that different?
Yeah.
Sum of
the squared loadings. That's what I have. Factor loadings. Let me look at my output.
I have eigenvectors and sum of column of loadings.
Yeah.
Eigenvalues and sum of squared correlations between factors / variable. So eigenvalues and sum of the squared correlations between the variables.
Let's see where it is on the output though. Yeah, I'm not ready. I'm sorry. I was looking to see where they are on the thing. Oh, here it is.
Sum of loading, sum squared.
So there they are. So they're on the total variance explained. It says initial eigen. Yeah.
Sum squared correlation between variables again. That's the eigenvalue.
And then the communalities is how much the item squared added across load on the component.
How much?
So how much each variable contributes to that component. So if you have a low communality, you have a variable that's not really contributing to anything, so it's not useful. It's not really correlating as much as it should to be useful. See how much better her writing is than mine? Okay. Oh, I forgot. The only assumption with factor analysis, principal component analysis, is that you're required to have a correlation among your variables. If there's no correlation, you can't really look at factors. You can't group the items into factors because there's no correlation there to group them.
Factorable.
They're not factorable. Does that make sense? Like if there's like zero correlation between everything, you can't really do a factor analysis or a principal component analysis. And you can look at the KMO/Bartlett test of sphericity, and you want that to be above 0.7 to have a good amount of correlation.
And factor scores, I think you mentioned that in class. Are each individual score times the loading.
Each individual score times the loading. Yeah. So it'd be like the strength of that factor for that subject. So if the factor was like openness, and they have a high factor score for openness, and like the 5-factor personality thing, then they'd be very open. Low neuroticism.
Each individual score
Times the loading.
So the raw score that they get
Yeah.
times the loading.
So it's like how you can look at individuals.
How each individual would
score.
for each factor. So if you think of like the 5-factor personality, like openness, neuroticism, blah 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 blah, and they would have a factor for each of these, so then they would tell you like how much openness they have, how much neuroticism. So it's good to see for each person. And also, we should talk about this. So why do we do rotation?
so we can get a higher relationship.
Yes.
On here.
Higher relationship. What do you mean by higher relationship?
Like an actual more picture of what the relationship looks like between factors.
Yeah, it simplifies and it strengthens the relationship.
It increases interpretability. I'm just reading off the book.
Very nice.
I think that's it.
Are we good in the factor analysis?
Oh, this?
Yeah. There's not a lot of
Factor now.
concepts for that.
Not much options to me.
I think we got everything.
That's everything that's on my list here.
Yeah, that's everything here. Okay.
Okay.
So you want to do path analysis?
Yeah.
Sure.
Okay. It's right there.
So what's the difference between PATH and SEM?
Latent.
Which one has what?
SEM has latent variables, and PATH analysis does not.
Path analysis only has measured variables. So it would be like take the homework
squares versus the circles.
Here's the homework example. You guys remember that?
Yeah.
This is,
Okay.
math, right? This is
Yeah.
what's going on.
What's that? What's going in the middle?
That's a correlation, right? The double arrow?
About a mediator.
Mediator.
Thank you.
Yeah.
And yeah, the double-sided arrow indicates the correlation.
Thank you for validating my statement.
I hear you.
Direct, indirect.
Yeah, indirect would be passing through. Oh no. I'm sorry.
Right on the
I'll buy you a new sweater.
Actually, the direct, Laura, would be not that arrow, it'd be the one below it.
It could be both.
It could be both. It could be the mediator.
Yeah.
Yeah, the mediator to this one is a direct effect.
Yeah, I guess directly.
The mediator being an independent variable, or being an X. I'm confused.
I thought mediator would be like a...
Well, indirect would be how this passes through here. So indirect would be the X to this Y.
Through the mediator.
This is a mediator. This is an indirect here. This is a direct. This is a direct. That's a direct. That's a direct. If this was just, you know, the outcome, if you were like cutting this off.
So that's the indirect.
What else? I don't know. So you'd have like an idea of your model, and you would try to replicate it with your data using only measured variables. So these are. So what are the ones that have arrows pointing away from them as opposed to pointing towards them?
Exogenous, right?
Exogenous. Endogenous and exogenous.
Wait, what?
So exogenous are the ones that have arrows pointing away from them.
Yeah.
Endogenous are the ones that have arrows pointing towards them.
So exogenous are outside.
Exogenous have arrows pointing away. Endogenous have arrows pointing to. So like the mediator variable and the DV would be endogenous.
Yeah.
Or the Y.
Yes.
You were talking about how your model works. We're like,
Oh, I mean,
we're going to talk about that.
I was saying that you could use this, you would get a bunch of data and you would try to replicate, see if this model fit the data. Same with any, like, path analysis, structural equation modeling, all that
Isn't
stuff.
there a thing for business with that? Or
Don't you, does the chi-squared
With path analysis, you could use, remember we did it in SPSS, but we did it with sort of a regression output. So you can use a regression output for like a more simple path analysis.
Yeah.
So, the RN SEA.
No, that's SEM. So this is, so while it's still a measured thingy with the picture, it's actually a regression. So basically, you take these variables in a regression and then you predict the mediator variable. And then you do a regression with all the variables in there, predicting the Y. And then you do a Sobel test to figure out if this is really a mediator. So it's more of a regression analysis. And for regression analysis, you can look at other stuff for fit.
Okay. Yeah. But when you start putting latent variables in here is when you would move to the structural equation modeling, which is when you would use like an AMOS program.
Yeah. AMOS, EQS, or Lisserl are the programs. And the fit indices are chi-square, RMSEA, SRMR,
Are we going to go over that?
CFI. Here, I'll start writing them out.
And this is for what?
Structural equation modeling. So it's more sophisticated path analysis with latent variables. So like if you're trying to measure resiliency or something. So it would look like So these are latent variables. Circle or oval is latent variable. Square is measured variable. E is the error for each measured.
Disturbances, they can also be called that.
And if I was to put something else up here with the same thing, then you can have correlations between the latent variables.
Is the arrow from a measure to a latent, is that causal?
Yeah, these one-way arrows are causal pathways. And again, you need a large sample size for this, like 10 to 20 subjects per item.
And so for this one, a significant chi-square is bad. Bad.
And what does that mean conceptually, like a bad fit?
That your model didn't fit what actually.
Your data?
Your data.
Yeah.
Yeah. So your
There's
model
a difference
doesn't fit
between
your
it.
data. You might need to adjust.
Yes.
Your data didn't fit the model?
So we have our parameters that we need to count. So we want to count the number of observations. And the equation for that the number of observations is equal to V plus 1 times V over 2.
What are the V variables? What does the V stand for?
Sometimes you use K, I think.
Yeah, sometimes it's K.
What is it?
I have V here. And a parameter is equal to a number of exogenous variables plus the total path. So you want your observations to have, you want it to
V
be,
is the measured variable.
yeah, sorry. I'll put that on here.
So like in this one we have 3. And then parameters is like
Is the boxes plus the arrows plus the disturbances.
1, 2, 3.
So what's the over-identified model?
When you have more observations.
Then parameters. So what's under-identified?
The other one.
More parameters. And the other one is when it's the same. So which is preferable?
Wait, isn't you said it?
K?
Over-identified is less parameters than observations, right?
Yeah, I said more observations than parameters.
Oh, okay.
Yeah.
Wait.
I was like, what?
Over-identified is less parameters than observations? Or more observations?
Well, I said more observations than
She
parameters.
said it right, but she
And then she said it the other way.
And then you said there's is it called just identified?
There's the other way to
Yeah, it's just identified.
Just identified, if it's equal.
Yeah.
Which is okay also. But you want it to be over-identified. You don't want it under-identified because there's really an infinite number of solutions for your unknown variables. So that's not ideal.
And under-identified is when you have more observations.
Under-identified is when you have more parameters. So it's more unknown than measured.
Yes.
Just a quick question. How long are you guys here for until you're done?
It's 7:20 right now. I don't know.
Oh,
We'll just finish and then answer questions and go home. I can give you time limit.
So we should keep going.
Yeah, we
So
should.
that's it for this one, I think.
Oh, we forgot the path coefficients for the. So again, for the path analysis, backing up path analysis stuff again. The numbers on the arrows, the actual path coefficients, are beta weights or squared semi-partials. So if I draw that model again, the arrows would be the numbers that you put on there would be the beta weights from your regression output or the squared semi-partials from your regression output.
What are they on structural improvement?
Whatever Amos tells you. they are.
What, sorry, what?
Whatever Amos tells you they are.
I think they're betas too.
I don't know.
So
I think it runs a regression.
It's just telling you the strength of the relationship then, correct?
Mm-hmm.
Correlation.
Well, it's actually a loading.
A loading.
It's
Yeah,
a
I was
loading
going to
here.
say it's an R. Or, yeah, it's a loading.
So it's kind of, remember loading from factor
Yeah.
analysis? It's the loading.
Yeah. Loadings are structural coefficients.
So how this variable contributes to this latent variable.
When you're talking about path analysis with the beta weight, semi-part, first of all, are those the same things? Beta weights when it comes
Isn't
to...
square semi-partial kind of better?
It is, I mean, it's not better, but it's a little bit different. It's like the unique contribution with the stuff partialed out. And then the beta weight is just like the standardized coefficient with the other variable called constant. So it's all the definitions we gave you earlier, the beta weights and the squared semi-partials. It's just applying them to the path analysis.
And that's the word path coefficient.
Yes. Path coefficient. The path analysis? It's SEM is like a more sophisticated path analysis.
I'm saying the path coefficient uses the same
No, you wouldn't do this with like or SPSS. So I think these are called loadings right here.
Yeah, they're loading.
They're not path coefficients.
Yeah.
They're loadings.
They're loading. And then
it's a little bit different because this is a latent variable.
Loadings or structural coefficients?
Structural coefficients they can be called.
Either one for
Yeah.
SEM? Okay.
And COVA? Yeah. Unless you guys want to hear more about
COVA or
Let's see, 1 dB, multiple IV, and C.
Okay. What are we doing? ANCOVA? So, we have 3 uses for ANCOVA. You can tell me if these are questionable or not. To reduce within group error. Questionable or not?
I don't know what that means. Questionable, like it's not true?
Like, I mean, is it a good use? Like, would you recommend using the ANCOVA for this purpose?
Sure.
Yeah. Sure. Yeah. It's okay. It increases the power if your covariate is related to your dependent variable.
Increases power if...
If you have your covariates related to your dependent variable, that's good, and it would increase power when you use the ANCOVA. So that would reduce the within group error. Another one is the quasi-experimental design. Say you had a non-randomly assigned group, gender, you can't really assign that, and using the ANCOVA to control for traits of that group. Is that questionable?
Yes.
Yes.
I guess it's questionable, like it's not the best way to...
Yeah, it's not recommended to use it, but a lot of people do. And the reason is because the assumptions that have to be met are easily violated when you use this for this purpose. And we'll get to the assumptions right after this.
You're manipulating the data in not really appropriate way.
Do you have to say something for this one that's not questionable or questionable? My notes are a little bit weird.
Let's see.
Yeah, okay, good. And then another one is substituting for repeated measures ANOVA. So in that you would have, so this is pre and post. And so you would control for pre So making these the same, making that constant between the two groups, and you're just comparing these two, if there's a difference between the post. So that's another way of using the ANCOVA. Yeah, you can control if these are different. Oh, I have another one. Step down in MANOVA. You won't go over that.
You want to?
I just mentioned it. Step down in MANOVA.
I'm sorry, the substituting for repeated measure ANOVA, is that questionable?
It's okay. I have your it's okay.
Okay.
It's okay. I don't really know why you would do it, but maybe to increase
If
power.
all your pre-test scores were like confounded or something, maybe you just want to get rid of them.
Yeah.
Maybe, or to increase power, maybe if you have some samples. I don't know, though. Because within group.
He didn't really give us examples for that.
Increase power, yeah. Just know this.
So for assumptions, we have our normality, homogeneity of variance, independence of observation, reliability of measurement, and
for reliability measurement.
independence of observation, not robust, still. We have a new one that's linearity between the covariate and the dependent variable. So, yeah, you pretty much just want a linear relationship, and you can look at a scatter plot for that. You could look at the residuals plot. Let's see. Homogeneity of regression slope across all levels of the IV, which is the assumption that's hard to meet when you have a quasi-experimental design.
Which one?
The homogeneity of regression slope across all levels. So for each group, your regression slope is going to be homogeneous. So if these two groups are inherently different, then that's hard to meet. So you guys know how to measure all that stuff. Let's see. Anything to add? I mean, ANCOVA is pretty much ANOVA, but covariate, so there's not too much there.
ANCOVA is like MANOVA.
We have the adjusted mean
For ANCOVA?
in the output for ANCOVA.
Adjusted mean?
Uh-huh.
Oh, that's,
So that's the means when the covariate is added, it's controlled for the model. So it's kind of parceled out, and so the means are adjusted for your groups.
Is it just that number to go down or up or?
It's not necessarily going in any direction. It's just being adjusted for removing that variable from the model, or partially out.
Like the CV parceled out, is that what you're saying?
Mm-hmm. Yeah. It's being controlled for, so it's held constant.
Just for the CV.
Yeah, just for the CV. So like that pre-being held constant in each of these groups.
You need a significant relationship between your CV and your DV. Significant relationship between your CV and your DV for it to be a covariate.
Okay.
Yeah, that's the linearity piece also.
Yeah,
A
part.
significant
Yeah.
linear relationship.
Exactly.
So if this is not correlated, then you don't want to use ANCOVA, because you're pretty much losing a degree of freedom when you don't have to. It's not necessary to use ANCOVA because the assumption is not met, and you're losing this degree of freedom, which artificially reduces your within-group variance for no reason.
What was that for?
So by losing this 1 degree of freedom, you're artificially reducing your within-group variance for no reason.
And that's for?
That's pertaining to linearity, the significant linearity relationship between the covariate and the dependent variable. And that assumption holds for MANCOVA too. I mean, this is all the same if you look at a MANCOVA, but with just multiple DVs.
Yep. That's pretty much it. Okay. That's all I have.
Okay, yeah, that's all I have too. Pretty short
The
one.
one where you look at the assumption that you look at the output in a special, was it homogeneous regression?
So
You would-
that's, yeah, that's like what I drew down here, where it's like you look at the DV-CV relationship at each level of the IV. So if you have gender, you look at the slope in male and female. So it's like, so you want them to look relatively the same. If they looked like that, then it would be a violation.
So you might do like a split
File thing.
since they split graph.
CSS, and then have a graph.
Because if the CV affects the different levels of the IV differently, then partially it will have a different effect on both.
Yeah, it won't be the same effect.
Very good explanation.
It's good when you put it in your own words.
Better
Okay.
in Dr.Gevirtz's words.
Make them your own. So now we can go to logistic. You guys okay with that? I feel like we just... Okay, only a little bit more to go.
All right, logistics.
So logistic is different because you have a dichotomous outcome. So that changes the curve to sigmoidal. What you have, sigmoidal. You've never heard of sigmoidal? It's non-linear. It's either yes or no, or dead or alive, or fat or not fat. I don't know. Oh, she drew her own.
I like that.
Maybe it's the way you said it.
Yeah, it kind of sounds weird. Like it sounds slimy, I think.
So since we have this, we have a lot of the assumptions that we've already been working with are not applicable,
Right.
since those are all linear model assumptions. So that's why all we have. Oh yeah, I'll tell them right now. We have the assumption is we want an absence of perfect multicollinearity. So we don't want all our variables to be collinear, like really, really correlated. So we look at the tolerance. We want an absence of perfect multicollinearity. We want no specification errors, which really would depend on your experimental design. You don't want any systematic things going on there. And independence of observation, which is good design also. So that's it. So that's a lot less. Easy to meet.
And we look at tolerance for multicollinearity. I forgot. What do we want that value to be?
Tolerance?
If we don't want, we want closer to 0.
But we always
We want it close to
want it
one.
close to 1.
Okay.
You always
Close to
want
1 means not
collinear.
collinear.
So with this, you're getting you're calculating the ratio of odds, which is the ratio of odds is equal to the probability of occurring over the probability of not occurring. Have you guys calculated stuff in this exam?
No.
Wait, the probability of what?
Probability of occurring over the probability of not occurring. And then there's that equation that calculates the probability of an event is equal to
Is it 1 over the
1 over 1 plus natural log negative a plus b squared. So this is what turns our sigmoidal curve into a linear function.
And this is the ratio of odds?
This is the probability of an event occurring.
predicted probability.
So what you would do is you have your A, your B, you have your variables, and then your slope here, and you would input it into this equation, turning this into a linear function. So that's the purpose of this natural log stuff. So it straightens out the curve. You take the natural log of your odds ratio and you straighten out that curve so it's interpretable.
Natural log of odds ratio?
the logic function. The odds ratio is useful because it can go from 0 to affinity. So it goes really high. We have our tests, which are, so for the output, Cox and Snell, the Nagelkerke, which are tests that test the
percentage variance.
Yeah, the percent variance in the
R
model.
squared in multiple regressions, kind of. They're the pseudo R squared.
Yes. And Nagelkerke is preferable because it goes from 0 to 1. Yeah, the percent of variance in the DV explained by the model. Pseudo. You guys remember that?
Which one?
The Nagelkerke and the Cox and Snell?
And same influence statistics, so Cook's, DF beta, those are the same.
Have your Cohen's kappa, is that in this section? Cohen's kappa, agreement statistic,
Agreement statistic, yeah.
corrected for chance. Log likelihood, how well the model is working, lower is better.
What did you say?
Which one? Log likelihood,
Right before that?
Cohen's kappa, agreement statistic,
Did you just curse?
correct for chance.
The classification table tells you about the hit rate. Percent even.
I'm sorry, so you're going to write the log likelihood? Is it 2 log likelihood is what?
How well the model.
This is what it is in the output.
Oh, yeah.
Yeah.
But you said lower is better.
Tells you how well the model's working.
So it's a better model.
Yeah, if your model is good.
But there's not like a certain.
No, it's not a certain value.
You use them to compare, you know, when you put different variables in, which is a better model. We have the Wald statistic. And so there's problems with the Wald statistic. Does everyone remember what happens if the B weight gets too large?
It's inflated the wall, so you type 1 error.
Yeah, it distorts.
Yeah.
If the B weight gets too large, so I think it's above 2? You remember? Okay.
I never knew what too large meant.
It's not going to be on the test.
It's probably good.
No, that it gets distorted if the B weight gets too large.
And so that's going to affect, you know, if things are significant or not. And you might want to take that variable out and see what happens to the model, you know, and see how much it distorts things.
That's all I have for this.
Does anyone have questions about any of
Does
that?
that increase chances of type 1 error? Or if it's inflated, or am I just making that up?
Let's see. So the B weight is big. It's divided by student error. It's inflating the statistic. So it's going to be significant when it's not.
Yeah,
It's going to appear to
yeah.
be significant when it's not.
So yeah.
Okay.
So type 1, yeah. So increases, right?
Not really.
Nobody cares about that.
Especially at this time. I wonder if that's even on still.
When I do my stuff.
Okay, let's move on. You guys can look at sensitivity and specificity on your own.
Alright. And then
What
discriminative.
are the terms? Sensitivity?
Sensitivity and specificity. Remind yourself about those.
Discriminative, kind of similar, a little bit.
So what's the
Kinda
difference between
different.
logistic and discriminant analysis?
Discriminant doesn't have to be recombinant? No, it does.
Discriminant, it's better to use, but it's more difficult to meet the assumptions. But if you meet the assumptions, okay.
Yeah, that's
Well, but discriminant, you could have more power with discriminant.
If you meet the assumptions.
Right.
If you meet- there's
but
more
you have,
assumptions.
but there's more assumptions, yeah. So that's what makes it kind of mixed.
yeah.
So you probably only want to use it if you had like a really small sample and you had like crappy power.
Yeah, and the predictors have to be continuous.
Yeah.
As opposed to with logistic, it can be dichotomous predictors.
That's what I was doing.
Yeah, that's where you are. But the outcome is still dichotomous.
Okay.
And you also still need a large sample size. We have all these fun assumptions back. Linearity, independence of observation, normality, homoscedasticity, all the good stuff. And then we have homogeneity of covariance variance matrices. And again, an absence of perfect multicollinearity.
Is it the homogeneity of variance covariance? Oh, that one. Never mind, that's the one used for boxes.
Yeah, that's really a box stuff.
That's a really long assumption.
I know. So for discriminant, you have, where are my notes? You have your canonical correlation, which is if you square that number in the output, you get the percent of variance that the discriminant function accounts for. So that discriminant function has all your predictors and percent of variance that is accounted for by your model.
Yep.
And that was what?
Canonical correlation that you square. And then we have structure matrix coefficients, which represent the correlation between the variable and the discriminant function. So it's pretty much the variable and the model.
I'm sorry. If you look at it on the output?
If you look at it on the output, it's called the structure matrix coefficient.
And what is that representing again?
So it's kind of like a factor loading. It's between the predictor and the function, discriminant function. It's like a factor loading.
And the lambda?
Yes.
So in between factor and what? Factor and...
Discriminant function. Just like go over your outputs that he gave out in class.
Yes.
I think there's one that he gave out with a nice little list.
What's lambda is that all of them?
We tested the canonical correlation is different from 0. So it's sort of like it's equivalent of like the F test and ANOVA.
It's like hyper correlation.
It's different from 0. So it's like kind of like the F and ANOVA. Probably.
That's probably good for discriminant analysis.
Yeah, it's really not too much knowledge.
Meta-analysis.
No, we're not going to go over that. I don't even think he put any questions on that. Yeah. You just read the handout. That's the only thing you're going to have to know about that.
Or
Yeah.
He's trying to acquaint us with the concept, right?
Yeah.
Yeah. There's not. It's not. I don't know.
I really don't know.
I doubt
He
it.
didn't. I mean, the concept wasn't even in the class last year, so we really doubt it.
Yeah, I doubt it, but you could just read that handout.
Yeah, it might be just
That
like.
wasn't that perfectly. That would be plenty of information.
So last is MANOVA. We have our assumptions again. Normality. It's late, that's why it's late.
You need to dramatize the concept.
Yeah. Normality.
Good.
Independence of observation. So you have linearity between the DVs. Is that what you have? That sounds weird to me.
So you want the DVs to be related?
Yes, you do. Okay.
So yeah, so correlation,
But not too related.
linear, strong.
Is it the same thing like 30 and 15%?
Well, yeah, because you don't want them to be perfect.
Yeah. You want it to be like in the middle. Just right. Homogeneity of variance, homogeneity of variance covariance matrices. So which of these assumptions would we look at boxes M for? And what does that cover?
Normality or homogeneity of variance covariance matrices, and then normality, linearity.
And Did you put it out there? Homogeneity of variance. So it's homogeneity of variance, homogeneity of variance covariance matrices, and normality can all be looked. I mean, if any of those are violated, you're going to get a violation of boxes M. But to look at, if boxes M is significant, you're going to want to do a little more in-depth analysis to see where the violation is coming from.
Mm-hmm.